So in this lecture, I want to talk about oscillatory loading of viscoelastic materials. And what we're going to do is we're going to develop the concept of the storage and the loss modulus. We're not going to talk about, at this time, their meaning. We're just going to come to the definition of them from what we know about hereditary integrals, okay? So let me begin by saying that we've already developed a description for viscoelastic behavior from creep compliance and a relaxation modulus perspective, okay? So let's see, we've already done this. So we've previously developed descriptions for viscoelastic materials in terms of creep compliance and relaxation modulus. We call creep compliance, remember we had that as J of T, and the relaxation modulus, which we said was Y of T, okay? So, typically, how do we find these, right? We've talked about this before. So typically, J of T and Y of T, right, are going to be obtained from creep or relaxation experiments. And these experiments are going to be experiments that require, let's say, times on the order of greater than 10 seconds, okay? So requiring times on the order of greater than 10 seconds. Okay? All right. So what about faster times that we might be interested in? Well, to characterize the response of viscoelastic materials over shorter times, right? Say, let's say less than 10 seconds. Okay? We typically are going to use oscillatory loads. Okay? So we'll say oscillatory experiments. Okay? These oscillatory experiments are going to give us some new quantities, but they are not telling us necessarily anything different about the material. They're of course related to the relaxation modulus and the creep compliance, but these are going to be a different representation. They're going to give us something called the storage modulus. And I'm going to call that Y prime, and we'll define that more formally later. It's going to give us the loss modulus. We'll call that Y double prime. And it's also going to give us the loss tangent, which we're not going to talk about in this lecture, but just for completeness, I'll remind you of it, which will typically be called the tan delta. Okay, so it's going to give us these three quantities. And what we hope to show is that they're related to, and we can use the creep compliance and the relaxation modulus to compute these, or we can use these to compute those quantities. Okay, so they're interrelated, but we want to talk about how to handle this so that we could characterize basically in any way that we wanted, either via traditional creep or relaxation experiments or via oscillatory loads. Okay, so let's begin. What do we do to start with? Well, let's just go ahead and write down the viscoelastic response to some harmonic strain function, okay? So let's say begin by considering the viscoelastic response to a harmonic strain function. Okay, so we know how to do that, right? Just recall our hereditary integral. So recall the hereditary integral for sigma of t, right, where we said sigma of t is equal to, and I'm going to use the Stieltjes formulation, negative infinity to t of y, the relaxation modulus, times t minus c, times epsilon dot, the strain rate, which is a function of c, dc. Right? Hopefully that's familiar to you from previous lectures. We'll call that equation 1. And like we have done previously, we're going to go ahead and decompose the relaxation modulus y into a time-independent and time-dependent component. Okay, so we're going to decompose y of t into a time-independent component and a time-dependent component. Okay? So how do we do that? We say that y of t is going to be whatever, some constant value, y naught, right? Plus, we'll call this second part y tilde to tell us it's time varying. It'll be a function of t. Okay? Let's call that equation 2. So hopefully this is all pretty straightforward. Now let's go ahead and introduce our harmonic strain function. Okay? So we introduce the harmonic strain function. Okay, and that harmonic strain function is just going to say that epsilon as a function of time is equal to some amplitude, call it epsilon naught, and then our harmonic term, which is e to the I omega t. Okay, let's call that equation 3. Okay, what is omega? Where omega is the oscillatory frequency. Okay. And it's given in terms of radians per second. Okay? And then I'll just, for formal definition, E naught is the amplitude. Okay? So hopefully that's all pretty straightforward. If you forgot, maybe you haven't done much with these harmonic functions in a long time, let me just remind you, I'll just say and recall Euler's formula, right? Euler's formula said that e to the I omega t is equal to cosine omega t plus I times sine omega t, right? So this is just a reminder. We're not deriving this here or anything like that. Okay? So what's our goal in this whole thing? Let me tell you, because it's not obvious yet. So here's our goal. So what we're seeking is the following form. So we seek a form similar to the creep and relaxation results. Okay, similar to the creep and relaxation tests, such that the following is true. Okay, so such that we could write sigma of t, so stress as a function of time, is equal to y star as a function of I omega, so this is a complex modulus now, times E naught e to the I omega t. Okay? Let's call that equation 4. Okay, so that's we're trying to find a form that looks like this. Remember when we talked about the relaxation modulus, we wanted sigma t is equal to y as a function of t times epsilon naught, right, for that particular loading. So we're trying to find a form that's similar to that. Okay. Okay, so just again from a definition perspective, y star is something we're going to call the complex, or sometimes it's called the dynamic modulus. Okay, we'll come up with its proper form in a minute. So to begin, what we want to do is just substitute equation 2 into equation 1. So we want to substitute that the relaxation modulus decomposed into the time-independent and time-dependent component into our hereditary integral. Okay, so substitute 2 into 1. Okay, and then we can write via the hereditary integral, sigma as a function of t is equal to this integral term, negative infinity to t of y naught plus y tilde, and now instead of t, it's going to be t minus c, since that's how we're evaluating this integrand, right, times epsilon dot dc. Okay? So that's pretty straightforward. Let's go ahead and now break out the integral in these two terms. This first term looks like y naught times the integral from negative infinity to t of epsilon dot, which I'll remind you is a function of xc, dxc, plus integral from negative infinity to t of y tilde t minus xc times epsilon dot, which is a function of xc, dxc. Okay? So let's continue down. This is y naught. This equation here now becomes, if we solve it, this is just epsilon of t minus epsilon evaluated at negative infinity, right? Then plus this integral term, negative infinity to t, y tilde t minus xc, epsilon dot xc dxc. Okay? What happens? What is epsilon at negative infinity? Well, everything in our viscoelastic modeling begins at time t equals 0, so this quantity is 0. Okay, and we're left with sigma as a function of t is equal to y naught epsilon of t plus the integral from negative infinity to t of y tilde t minus xc epsilon dot of xc dxc. Okay, let's call that equation 5. Okay, now let's substitute our harmonic strain function into equation 5. Okay, so substitute 3 into 5. Okay, and when we do that, we have sigma as a function of t is equal to y naught times now epsilon naught e to the I omega t, okay, plus the integral from negative infinity to t of y tilde t minus xc. Okay, and now what's epsilon dot? What's right? This is epsilon right here. So what's epsilon dot? That must be the prefactor epsilon naught, and then the derivative will just be times I omega, and then times e to the I omega t. Except it's not t, right? Because it's a function of xc now, so it's actually xc, and then dxc. Okay. So epsilon naught, I, and omega are not variables of integration, so we can pull them outside the integral, and so that we can write sigma as a function of t is equal to y naught epsilon naught e to the I omega t plus e naught times I omega integral from negative infinity to t of y tilde t minus xc times e to the I omega c dxc. Okay? Let's call that equation 6. Okay, so where are we at now? Well, remember what we're trying to do, right? So remember that recall from equation 4. That's the form that we're trying to seek. So recall from equation 4 that we're trying to find. We're looking for a form that looks like sigma of t is equal to y star, a complex modulus as a function of I omega, times epsilon naught e to the I omega t, right? So what do we need from equation 6 to get there? Well, we have this term here on the this first term is epsilon naught e to the I omega t. That matches there, but we have epsilon naught here, but we don't have e to the I omega t as a coefficient, right? So we need to have that somehow, right? So we need an e to the I omega t term for the second term in equation 6. Okay? So how do we do that? Well, we're going to introduce a change of variables. So we introduce a change of variables, okay, which we're going to say that eta is equal to t minus xc, and correspondingly then that d eta is equal to negative dxc. Okay, so let's go ahead and call those equations 7. Okay, so if we do that, then the integral term in equation 6, okay, so the integral in equation 6 then becomes, right, so we have this integral that says negative infinity to t of y tilde t minus xc e to the I omega xc dxc, right? What does that become? Well, let's look at our limits of integration. So we still have an integral here. When xc is equal to negative infinity up in here, then eta becomes infinity, so let's write that. Eta becomes infinity. And then when xc is equal to t, then eta goes to 0. So we go integrate from infinity rather up to 0. And now y tilde is now evaluated at eta. And how about this exponent? We have e to the I omega xc. So if we solve for xc, that looks like t minus eta. So this is e to the I omega t minus eta. And then now dxc is equal to negative d eta. So negative d eta, right? So we're pretty close there. What do we need to do? Well, let's note that this, if I swap the limits of integration, instead of going from infinity to 0, I go from 0 to infinity, then I just change the sign of the integral, which cancels out this negative sign, okay? So I can write that. That's going to be equal to now integral from 0 to infinity of y tilde times eta times e, and I'm going to expand this out to the I omega t e to the I omega eta negative d eta. Okay. Note that the variables of integration are not either omega or t, so we can pull that outside the integral and write that this is e to the I omega t times the integral from 0 to infinity of y tilde times eta e to the negative I omega eta d eta. Okay, let's go ahead and call that equation 8. Okay, so we're almost there. I'm going to go ahead and expand this integrand using Euler's formula. Okay, so expanding equation 8. Okay, using Euler's formula. Okay, I'm left with, I have this e to the I omega t, and I'm going to leave that. I'm not going to expand that part from Euler's formula because that's what we were trying to seek, right, for our form that we wanted. But inside the integrand, I'm going to use Euler's formula. And this becomes then y tilde times eta, and then this becomes the cosine of omega eta minus I times the sine of omega eta. Okay? D eta. All right? So that, it's not really an equation. I'm just going to label it 9. That's the expansion of this last term. Okay? So how about I say substituting 9 into 8 and 8 back then into 6. Okay? So let's just say substituting 9 into 8 and back into 6. Okay, now I'm back to this equation that says sigma of t is equal to our first term, which is y naught epsilon naught e to the I omega t, right? And then I have plus that term I omega epsilon naught, and then I now have this quantity here, which is e to the I omega t times this quantity here, right? Times the integral from 0 to infinity of y tilde of eta times the cosine of omega eta minus I can pull that side of the integral. Integral from 0 to infinity of y tilde of eta times sine omega eta. And I should go back and put a d eta here as well. D eta, and then a minus there. Okay, let's call that equation 10. Okay, now what I want to do in equation 10 is I want to factor out the E naught e to the I omega t. Okay, so factoring E naught e to the I omega t, and then distributing the I omega term right here, right? Then what we can end up with is sigma as a function of t is equal to this quantity that is, I'm going to put it in parentheses here so I can separate the real and imaginary parts. So this first term is just then y naught. Okay, so when I distribute now this I omega term into here, then this I omega multiplies a real, so this becomes imaginary. But when I multiply I omega times the second integral, I times I is I squared, which is -1, which cancels out the negative there. So I'm left with a real. So this becomes plus omega integral from 0 to infinity of y tilde of eta times the sine of omega eta d eta. Okay? So that's the real term. And then I have a plus I omega times the integral from 0 to infinity of y tilde of eta times cosine of omega eta d eta. Okay? All of that times our factor, which is epsilon naught e to the I omega t. Call that equation 11. Okay, so we're getting close now. So we have basically what we want. We have this of a form some quantity, some complex quantity, times E naught e to the I omega t. So this complex quantity must be the complex modulus y star of I omega. Okay, so let's say that we revising equation 4. Okay, what we want is equation 4, remember, was sigma of t is equal to y star of I omega times epsilon naught e to the I omega t, right? Well, what is this term y star equal to? What's any complex variable? How do we write that, right? So, okay, so we can write that as y prime, which will be a function of omega, plus I times y double prime, which will be a function of omega. Those aren't derivative terms. Those are just real and complex coefficients inside the complex modulus, times epsilon naught e to the I omega t, right? So we could write then that y star of I omega is going to be equal to y prime of omega plus I times y double prime of omega. Okay, let's call that equation 12. So now what we can do is we can just compare equations 11 and 12. So comparing 11 and 12, right? We can just read off the quantities, right? What must y prime of omega be? Well, y prime of omega is just the real part of equation 11. So that's y naught plus omega times the integral from 0 to infinity of y tilde eta times sine of omega eta d eta. Okay? And how about for y double prime? Y double prime, function of omega, is equal to omega times the integral from 0 to infinity of y tilde of eta cosine of omega eta d eta. Let's call that equation 13 and equation 14. Okay? So now all we've shown is that we can come up with a complex modulus, and we just define these terms. Okay? So we define the following. We say that y prime, we define that as the storage modulus, and we define y double prime as the loss modulus. We'll show in a couple lectures why that's called the loss modulus. It turns out that the loss modulus is proportional to the amount of energy dissipated during oscillatory loading. I want to give you one final remark, though, before we close. So here's a final remark. What do you notice about equations 13 and 14? Well, we are getting a storage modulus and a loss modulus, which we can combine to give us this complex or dynamic modulus. But you'll notice that it's completely defined. Remember, y tilde is just the time-dependent portion of the relaxation modulus. So both of those are completely defined by the relaxation modulus. We haven't introduced any new information. We're just presenting it in a different way that's more convenient for oscillatory loading. Okay? So I'll just say that note from equations 13 and 14 that the complex or dynamic modulus y star is a function of I omega, and its components y prime and y double prime are completely determined by knowing the relaxation modulus, y of t. So that's on one hand it's sort of surprising, and on the other hand it's not, right? It does convey all the information, but it's casting it in a different form. So what you might expect now is that, well, if I know the storage or loss modulus, I can probably compute the relaxation modulus, and you'd be right, and that'll be the topic that we'll talk about in some future lectures.